Do 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 do. Hello again. I hope the other day's fundamental theorem went great. That's all we're covering again today. Just a couple more examples. Make sure you feel good about everything. Do some applied examples as well. Something to keep in mind, I think, whenever you're doing integrals, even the indefinite kind. That problems might give you the function in a bad form. What I mean by this is it helps a lot to simplify. The function before you try to integrate it. An example of this is something like, give an example, something like square root of 8x times 1 over x plus e to the x to the 3/2. Yeah, this is crazy, but it's actually integrable. You're going to save yourself a lot of effort by simplifying the inside. Actually, simplifying the whole thing. Because really the 8, the square root of 8, I can write as an 8 to the 1/2 out front. And then x to the 1/2 on the inside. 1 over x, as always, we'll call that one x to the -1. And then, you would want to simplify this even a bit more. So 8 to the 1/2. And so that's x to the 1/2 times x to the -1 is really x to the -1/2 plus x to the 1/2 e to the x to the 3/2 dx. And so this is just the power rule. But this is going to be u substitution. And you'll just want to get in the mood of recognizing that every time there's a plus sign, try to get that plus sign in a place that you can kind of split the integral into two integrals. That's kind of what we did here. Because at the beginning, the plus sign was sitting in the middle of parentheses, which is not great. But over here now, the plus sign, this is two integrals now to a certain extent. Right? It looks something like that if we want to think about it that way, which I'm not going to right now, but you know what I'm saying. So let's do that. Let's just approach this one more time. 8 to the 1/2. If I use the power rule on x to the 1/2, that gives me x to the -1/2 plus 1 divided by -1/2 plus 1. And then the second piece is really 8 to the 1/2. I'm going to use u substitution with u equals x to the 3/2. So then du is going to be 3/2 x to the 1/2 dx. And I can rewrite that as really 2/3 du is x to the 1/2 dx. So this is really 2/3 e to the u du. So this simplifies to 8 to the 1/2 x to the 1/2 divided by there, that's a 1/2. 8 to the 1/2 2/3 e to the u plus c, and I can substitute u back in. U was x to the 3/2. So this is really 2 square root 8x plus 2 square root of 8 over 3 e to the x to the 3/2 plus c. So that's an example of where you're going to save yourself a lot of effort just by simplifying things out front. I realize that wasn't exactly a definite integral, and we were looking for areas, but just in case things like that show up, you're going to want to, you're just going to want to keep that in mind. So let's do one of the, maybe a tougher problem now. Or an applied problem, right? An applied example. And really what I want to stress here is that area is a relative term. So when we calculate area under a curve, carries the units of the x-axis and y-axis multiplied together. So how can we think about that? For example, if I'm given the velocity that a car travels at a certain time, the velocity that my car travels, didn't want it like that. I want a bell curve here. Velocity that a car travels over time. So this is the velocity a car has over time. This is t in seconds. This is the velocity in meters per second. Then the area here call this T1 and call this 0 T0. Then the area under the velocity curve carries units of meters per second times second, and of course if you're per second and then multiplying by seconds, it carries units of meters. So sometimes area is indeed a meters squared. That's how we would calculate area on the ground, but the area of a graph does not necessarily have to be the same. In this case, the area itself is actually meters, and indeed the area calculated gives the total position, the total distance the car travels from T0 to T1. That's how we want to think about these applied examples. It's to a certain extent you're calculating the area under a curve, but really what you're doing is you're multiplying the units of the y-axis and the x-axis, and that's what you're producing out of something. So I'm going to do that when I bring up the applied example. This is applied example 6 from the book. So it says the population growth in Clark County. If COVID keeps up, we'll have to change this to population decline. That was a morbid joke, but bear with me. Population growth in Clark County. So it says as the 20th century ended, Clark County in Nevada, dominated by Las Vegas, was one of the fastest growing metropolitan areas in the United States. From 1970 through 2000, the population was growing at a rate. Population grows at a rate of RT equals 133,680 T squared minus 178,788 T plus 234,633. This is valid for T between 0 and 3, where T is measured in decades. So this is people per decade. Valid for 0 less than or equal to T less than or equal to 3, with T measured in decades. So basically, from 1970 to 2000, we have this growth rate. The question then asks, what is the net change in population from 1980 to 1990? And really, T0 is 1970, and T equals 3 is 2000. So this is really asking us difference between T equals 2, T equals 1 and T equals 2. So it's asking for the net change in population. Now, this is the special words. Net change in population, it's not net change in the rate of population, right? So R is given in people per decade. We notice that people per decade times decade equals people. And when you think about it like that, people per decade times decade equals people, then you get an idea. This is really us calculating the area under R of t. Or in other words, we're just supposed to interpret this as the definite integral from 1 to 2 of R. So if we do that, it's not too hard. We just basically copy paste what we have here. And we can use our power rule on each piece. Power rule, I'm going to be dividing 133,680 by 3. And I get t cubed minus 178,788 divided by 2, t squared, plus 234,633 t. And then, since this is a definite integral, I'm going to have to evaluate at my bounds. That's the one special thing here. Notice I didn't add that plus c. Hopefully you guys are getting used to that you don't need it for definite integrals. And so I just plug a 2 in, and I subtract plugging a 1 in. So I'm going to write it maybe in a little weird notation. I'm going to write this as 2 cubed minus 1 cubed. Hopefully you guys can see why this still works. 2 squared minus 1 squared plus 234,633, 2 minus 1. And if you go ahead and calculate that out, we get that the population increased by 278,371. What's my units? Well, that's the whole point of this. The units is people. So that means we increased population by this much from 1980 to 1990. So that's how you can apply these definite integrals to applied problems instead. I don't think there's anything else I wanted to cover. So just keep in mind that areas under curves don't always equal area in real life. It's not just meters squared or feet squared or something like that. There's some more special things that you can calculate with areas, and that's the way that people actually apply all of this, because that's where we get all the information from a lot of times. Okay, that's all I have. I hope you guys have a great weekend. I'll see you all on Monday. Oh, as of today, I will have uploaded, today being the day when this comes out, which I believe is April 3rd. Yes, April 3rd, there will be a practice exam on Canvas, and it will be exactly in the format that the real exam will be. And you're going to need a special code to get into that practice exam. Special code will be the word practice, all lowercase. And basically, I'm not going to be very lenient on the real exam about you guys not being able to figure out how to upload things or input answers, because I'm giving you this practice exam. So do everything you can. If you're worried about uploading or entering answers on these exams, do everything you can now, because I'm not going to be lenient come the actual exam. So I'll send an announcement in Canvas with the same thing. But anyway, that practice exam is in Canvas, and it'll be open for you through next Thursday, which is when the real exam opens. So go ahead and try it. See if you can get some nice responses. I'll see what your responses look like too, and then I'll make sure to make an announcement before the real exam about how everything's going to work perfectly. So that's all I have now. Have a great weekend once again, and stay safe and healthy out there. See ya.